Okay, this video is for my student Michael over at Columbia University, and he wanted to go on over sketching graphs of both the derivative and the second derivative given a function. So when you're given a function, f of x, what you want to do is inspect two things. So graph of f of x, or f of x graph. The first thing to note is you want to inspect the slope. Basically intervals where the function is increasing or where the function is decreasing. The reason being is where the function increases, that implies that the first derivative will have a positive value, and when the function decreases, that's when the first derivative has a negative value. The other thing that you want to do is you want to inspect something known as concavity. Concavity looks like this. So when a graph is concave up, it has this kind of curvature to it. It means the rate of change of the slope is increasing. Like if you're to be in like a, I guess you could say a fighter jet, and you're headed straight down, and if you pull up on the stick, the steepness of your ascent, it's going to start leveling off, but then it also starts to increase in the other direction. That's what concave up means. Basically means where your second derivative has a greater than 0 value. When you're concave down, it's the other way around. Suppose that you're in a fighter jet and you push down on the stick to level out. So your slope begins to steepen less, and then it starts to steepen more in the negative. So steepening less in the negative and then more in the positive means concave up. Steepening less in the positive as you progress and then more in the negative means concave down. You could also think of this when something's concave up, if rain were to fall, this acts as more of a bucket. And when something's concave down, if rain were to fall, this acts more as an umbrella. Okay, so those are two things that you can take a look at for how curves look. Something known as an inflection point is when the second derivative is equal to 0. And that's when a concavity, point of concavity changes. So like you could say something goes from concave up to down. So you might have like a function like this. You might have concave up, and then this point of inflection comes in and says, nope, we're going to go concave down. Or the other way around, it might go concave down, and then here's a point of inflection, and then make it concave up. The reason, like when we look at the concavity, if we have the graph of the first derivative, we know when something's concave up, because when the second derivative is greater than 0, that pretty much implies that the first derivative is increasing. Or you could say that its slope is positive. And then when the second derivative is less than 0, you can actually say that the first derivative is decreasing, or the slope is negative. So let's just go through an example. Alright, so suppose my function looks like this. I have something like that. Okay? So this looks like a general polynomial. A polynomial has a certain amount of degrees. It really depends on how many terms that you have. Actually, you know what? I'm going to go ahead and start with something easier. So let's just start with something that looks like a cubic. So right here, if I were to have a cubic and it would look like this, I'm interested in drawing the graph of both the derivative and the second derivative. So the very first thing that I want to do is I want to take a look at my original graph, and I want to mark off very key points. First are critical numbers. Notice that at point A, the slope at that spot is 0. And then notice at point B, if I just use those values right there, the slope is also 0. So at A and B, if the slope of the function f of x is 0, that would mean that the first derivative at A and the first derivative at B are both equal to 0. Because whatever the function's slope is, gives us the derivative's value. Slope of the function, value of the derivative. So if we were to go onto the derivative's graph, at point A, we would have an intercept. And then also at point B, we would also have an intercept. Okay? So those are two key points that we could draw for the derivative. Also, notice that before A, notice that the function is increasing. The slope is very steep, and then it starts to level off. So what you could do is you could say, if the slope is very steep in the positive, that means the function, the derivative had a very positive value. So like if we were to go on over to like a value of d, the slope was really high, maybe like a positive 5 or 6. So then at point D over here, if we had a value of 6, we could draw a value here. And then notice that as you move toward A, the slope begins to lessen. So that means the value of the derivative begins to lessen. And then eventually it will intersect at A. Notice past A, the slope begins to steepen in the negative direction. It starts to become a little more negative and a little more negative and negative. So that means after A, the value of the derivative is going to be negative. There is a very key point right here. I'll go ahead and mark it like so. Notice that the graph kind of has this concave down feeling, and then the graph also has this concave up feeling. This point right here, if I labeled it C, is something called a point of inflection. And point C, if you were to go ahead and draw that on the derivative graph, a point of inflection is also technically like a maximum or a minimum of the derivative. So notice that the slope begins to steepen. It's like -1/2, -1, -2, -3. So then right at C, it looks like it's at -3. But then the slope stays at the same value, and then it starts to lessen back to 0. So that means if you were to draw, the values of the slope along the derivative, or the values of the slope, along the function or f prime of x, you would actually get this type of curve. So a point of inflection is basically like a minimum or a maximum of the derivative. Second of all, then we notice that notice that the slope begins to lessen in the negatives, becomes 0, and then goes back to being positive, and then it becomes really steep. So that means the slope goes from being negative, intercepts point B where it's 0, and then it starts to become more positive. So the derivative has more or larger values, and this is our graph. If this was a cubic, then this guy's derivative is a quadratic, and notice that it looks like a parabola. If we had to draw the second derivative, well, we know that at point C we have that point of inflection, and the second derivative is basically the derivative of the first derivative. Notice that the first derivative has a slope of 0 at that point of inflection. So that means the second derivative has an intercept at that point of inflection. You can also do this. Take a look at the curve. Notice that it was concave down, and then it goes a concave up. So that means the second derivative should have some negative values here, and then it should have some positive values beyond, because it went from concave down for the function, and then the function went to concave up. You could also just use the graph of the derivative to find the second derivative's graph. Notice that the slope here is negative, but it lessens to 0. So that means the value of the second derivative is negative, but then it approaches 0. And then the values of the slopes begin to pick up. They start to become ever increasing in the positive. So then that means after the value of C, the second derivative has a positive value. And then this is what the graph would look like. This is just like a rough sketch of those dots. You don't really have to plot those points. But another thing to mention, if you do the second derivative, well, if it's the first derivative was x squared, the second derivative would probably be something around like 2x. Or if you did the derivative of x cubed, you'd have like a 3x squared. This guy would be a 6x. But what if we didn't know the coefficient in front? We just can say that's like something that involves x squared, something that involves an x, and x is a line. So then that gives you a good hint that you're going to be drawing a line like so. Okay. So that's how you do the graphs going forward from the function to the derivative to the first derivative. If you had to do the other way around, so suppose that you were given, suppose that you were just given the derivative, and the derivative looked like, let's see, I guess we'll just do it. We could do another parabola, but we can actually, let's just do this. So it's another cubic like so. So if the derivative looks like this, notice that the derivative has an intercept, and I'll call that point A, I'll call this point B, and I'll call this point C. So if we were to look at the function at point A and B and C, those are very specific points. When the derivative is equal to 0, we're dealing with an extreme value. Notice that the value of the derivative went from positive to negative, which means that the function should have gone from increasing and then to a 0 slope, then to decreasing. that lets you know that point A is something called a maximum. How you draw a maximum, and we don't really know where the function starts, but you could just put a point as clear as day right here, and then you could draw it kind of curving like so, okay? That lets you know that you've been climbing up, you've been increasing, you reach a high point, and then you decrease. Notice B is the opposite. The value of the derivative is negative, then it becomes positive. That lets you know that your function was originally decreasing, then it maintained a zero slope, then it goes to increasing. This is known as a minimum. So how would you draw that? You just put some point down for B, and then you can go ahead and draw a little curve like this. I'm not going to connect these yet. Notice that the first derivative has a minimum right here at this value. I'll call it capital D. That's the first derivative slope is 0, which means that the second derivative is equal to 0 at a value of D. When the second derivative is equal to 0, that's called an inflection point. And how to draw an inflection point on a graph? Well, you would expect, like, here's a graph, it kind of has that concave down feature, and then at point D, you would switch the concavity. You don't have to have this intercept, it doesn't have to be there, but just put a point inflection at that x-coordinate, okay? Moving on, so notice that I'll call this point E, right about here. Notice that the first derivative also has another maximum where its slope is 0. So that means the second derivative at E is equal to 0, which means we might have another, well, we will have, not might, we have another point of inflection. So if I wanted to draw a point of inflection at E, what I have to do is I have to make sure that this curve is concave up, and then maybe at this point then it becomes concave down. Also look at C. Point C on the graph of the derivative, the value went from positive to negative. That means we went from increasing, zero slope, and then decreasing. So this guy is known as a maximum. So if we put some sort of point over at C, we would say that this is a maximum. So this is what the graph would look like. This guy looks like a negative x cubed, plus some other shit. This guy would be the opposite. Like if we were to go backwards, we would increase in power. So we'd probably have a negative x to the fourth plus some other shit. If we were to graph the second derivative, though, how do we graph the second derivative? Well, we know that the first derivative had a minimum at D, so here's point D, and then a maximum at E. Those were extreme values. When the first derivative had a slope of 0 at D and E, the second derivative has an intercept. And then notice that the graph of the first derivative, we can take a look at when it's increasing or decreasing. Notice before D, the slope was negative. So then that means the value of the second derivative is negative. Notice that from D all the way to E, that slope is positive, and it may increase like so. That means the derivative is going to, the second derivative is going to have that positive value. And then notice that after E, the slope went to 0 and then became negative. So that's what it would look like. If we took the derivative of a negative x cubed, we would have somewhere like a negative x squared plus some other shit. And that's how we would make that graph. So that gives you an idea of how to work from a function to both the first derivative and the second derivative. Or if we had a first derivative, we can go back to the function and then to the second derivative. Always keep in mind, what kind of function you might be dealing with. If you have a polynomial, take a good guess at what the highest power is, and then it can give you a hint on how you can make a drawing or a graph of like what the curve should look like. Okay, I hope that helps.